There are some notes for the first two lectures this morning already posted on the website by the schedule and the list of speakers. There are notes in the file, and we will make posting notes on a regular basis. So that anything which was unclear during lecture can be reviewed. Yes. Sorry? Maybe in the case of some of the speakers who are incredibly well prepared, perhaps obvious intent, but otherwise that seems perhaps unlikely unless one of them is very well. Anyway, we have Uri Brezner who will be talking to us about the derived category and Beilinson propositional planning.
Abelian category and okay, so I will talk about the derived category of an abelian category, and then hopefully some about the derived category of coherent sheaves, the bounded derived category of coherent sheaves on Pn. Okay, so let's start. Let A be an abelian category. Keep in mind we have given a variety. We have 3 of those actually, but the 2 that will interest us are the one of quasi-coherent sheaves and coherent sheaves, or more generally just modules over some ring. And given this abelian category, we can form the complex category, the category of complexes, which category of complexes. That is, the objects are just complexes of objects from the abelian category. Morphisms are just morphisms of complexes. From this category, we have a bunch of functors, which are the cohomology functors. Now, when we go to the cohomology, then obviously we lose some information. Given a map between the cohomologies, we can't always pull it back to a map of complexes and such like. So we would like to find something better to work with, something that we can have all the information of the cohomology on the one hand, but we'll be able to work between them. And we do this in 2 stages. So the first thing we have to remember that between complexes there are homotopies. And we know that homotopies give the same maps on the cohomology. So we define, our next step is to define Ka, which is the homotopy category. Its objects of Ka are just complexes, but the morphisms in Ka are now between 2 complexes are the morphisms of complexes with equivalence classes with respect to homotopies. And we get so already we're better off, but that's still not enough, because if you recall, we have quasi-isomorphisms, which are morphisms of complexes, which are not necessarily homotopy equivalences between the complexes, but which do induce the same maps on the cohomology. So the second step is to formally invert all quasi-isomorphisms. So now we define the derived category. Its objects, again, will be just complexes, but the morphisms will be obtained from formally inverting quasi-isomorphisms. That is, if we have two complexes and a third one, and maps F and Q, and F is just any homotopy class of maps, and Q is a quasi-isomorphism, then we would like to think about it as a morphism in the derived category, that is, to take the formal inverse of Q. And then composing such roofs and so on. However, in this setting, we are pretty lucky that actually any morphism is just a roof. That is, if you have compositions that is two roofs, then there is one roof that lies over them both. So there is just, all morphisms are just roofs of K. Pardon? Roofs in K, yes. That is one quasi-isomorphism and one homotopy class. Okay, so this is question? No. So this is just a localization process. That is, we started with CA, or actually with KA, and we have a functor that goes to the derived category. We can call it PA. And if we have some category D and F such that all quasi-isomorphisms are mapped to isomorphisms in D, then there exists a unique functor that such that this diagram commutes, and dA is unique and up to equivalence. Okay. So, yes. The condition is F that it takes quasi-isomorphisms in Ka to isomorphisms in D, which is just the usual universal property of the localization of a ring, just translated into categories. Okay, so we have 4 categories now. We started from A, we went to the complexes, we went to homotopy, and ended up at the derived. We started from an abelian category. The complex is again abelian, which is very easy to see. However, the homotopy and the derived categories are in generally, actually usually not abelian. There will be abelian only for a very simple abelian category A, but they are just additive. So dA is an additive. Additive category. That is, we lost the notion of an exact sequence, which seems kind of odd as we're talking about taking cohomology, and there has to be something that corresponds to the exact sequence, because short exact sequence in A corresponds to a long exact sequence of cohomology. So it seems that there's something missing. And that something that's missing is the triangulated structure with and triangulated. Yes.
What category to be additive?
Again?
What does additive mean?
Additive means that the homes are abelian groups, and the composition is bilinear, and that there are direct sums. Not necessarily kernels, co-kernels, first isomorphism theorem. So there is no really notion of an exact sequence, because morphisms don't necessarily have kernels and images and the like. So what is a triangulated category? Well, it's a collection of sequences that we would like to think of them as the exact sequences. That is, we need to add some information. We need to just take it by hand and remember what are the exact sequences. So in the category of complexes, and in particular in the derived, we have the shift functor from dA to dA, which is which takes a complex to a new complex, and n place it's xn plus 1. That is just shifting the complex to the left, and the differential is minus the differential of x. And don't worry about the sign, it just all works in the end. Okay, so this is, we have the shift functor, and it is an invertible functor, so we can also shift -1 in the other direction, and we can shift several times, and the like. A triangle is just three objects and three morphisms, but with one jumping in the degree. You can think about it as x goes to y, goes to z, then goes back to here, but with the shift. And these are our candidates for exact sequences. Out of them, we need to choose some that we will call exact or distinguished, which will be the exact sequences. And of course, a morphism of triangles is three maps between the objects, and then a fourth one, which comes from the shifting functor, that everything commutes.
Modern?
Yes?
Theoretically, there could be a notion of an exact sequence, because you say that some of the kernels do exist.
Yes.
So we could define, if you have a sequence where the kernels exist, then we could do that. So
the point, we'd like to have it a sort of a natural triangulated structure, because a triangle structure is just something added to an additive category. But we would like one that will preserve the exact sequences from the original category. That is, every short exact sequence from A will be an exact triangle in the derived.
this doesn't happen if we consider only sequences.
Yeah, it's not enough. Okay, so next we want to talk about the mapping cone. So given a map, x goes to y, f, we want to form the mapping cone, which is a complex, f, and such that at the nth degree it's yn xn plus 1, and its differential is yn xn plus 1, yn plus 1 xn plus 2. We have the differential of y here. We have the differential of x here with the sign, and we have f going here. That is, we can write it as a matrix Note that the cone comes along with two natural maps. The first one is just taking y into the first summand, and beta is just the projection onto the second summand. So we have this, and we declare all triangles of the form triangles of the form exact. Okay, so and the set of all such triangles satisfies several axioms, such as we saw, every morphism can be completed into an exact triangle. We have to close it under isomorphism, so that's kind of obvious. And basically, they satisfy everything that we need to have a good analog of exact sequences. So as a result, we have analogs of the 5 lemma, of the snake lemma, of the splitting lemma, and of the long exact sequence of cohomology. Basically, everything we need, we get from this. And the point is that if we start from a short exact sequence in A, we can push this everything to the derived category. That is, we consider each object in A as a complex which is only at degree 0, concentrated at degree 0. We get y, z goes to x1, an exact triangle in the derived category. And then if we apply the cohomology functors, then we get the long exact sequence of cohomology. The interesting part is that the map in the snake lemma goes from hi then to hi plus 1 x. The map here is exactly the one that naturally arises from taking cohomology along this exact triangle. So we get a lot of things that usually work quite hard for, basically for free, just because we're hiding all the machinery somewhere behind it. Amit, till when do I have? Okay, so. Oh, great. Also, we can have the bounded derived. Which is even easier to work with. which is the full subcategory of the derived category, which consists only of complexes that have bounded cohomology. The full subcategory consisting complexes with bounded
In what sense bounded?
that the cohomologies are all zero for high enough and low enough I. Note that the complex itself doesn't have to be a bounded complex. As an example, if you have an object and you take an injective resolution, then the resolution is not necessarily a bounded resolution, a bounded complex, but its cohomology is. If though for the original object it was. No. Okay, so let's have an example, and we'll throw in a bit about derived functors along the way. And then we'll continue on to coherent sheaves.
Can you remind again, what's the advantage of looking at bounded?
It's easier to work with especially when defining functors. In the unbounded setting, the derived functors right-left are not necessarily exist. In the bounded, it's usually pretty obvious that they are. Actually, I think that given a nice enough abelian category also in the non-bounded, but it's newer and a bit more technical to show it. Okay, so let's add an assumption A, an abelian category with enough injectives. Now consider any short exact sequence that any object can be embedded into an injective object. Now the question is, what's an injective object? Or is that okay? An injective object is an injective object is an injective that whenever you have an embedding and a map here, then you can extend it. That's an injective object. Enough injectives is that any object can be embedded into an injective object.
Which one is the injective?
I. I is the injective. Pardon? In which category? Q, if you look at abelian groups, Q. Home to Q. No, okay, never mind. So we have a short exact sequence. Let's give these fellows names. Now we can consider everything in the derived category. We can form complexes, and we can form the following complexes. This will be the degree 0, so we have the complex which is just z at the 0 degree. X goes to y through f goes to 0, goes to 0, and x 0, 0. Obviously, there's the identity map here. And obviously, there's G here. So we have 3 complexes and 2 maps in CA or KA, whatever. The point is that this map is quasi-isomorphic. It's a quasi-isomorphism. If you take a minute and think about the cohomologies, then this is just a quasi-isomorphism. And now here we shifted X, so we can invert this map. So we have a map from this complex to this complex and then to this complex. So what we got here is a map from Z to X shifted by 1. If you recall, the X group of Z and X is exactly the group that classifies all extensions of Z by X, which is short exact sequences of the sort. That is, we obtained a map X1 ZX into home in the derived, bounded derived actually, ZX1. Now, replacing X over there with some injective resolution and a bit of diagram chasing shows that this is in fact an isomorphism. Furthermore, there's nothing special about 1 here. This actually extends to X n in A, is canonically identified with Z shifting of n. Yes? X is the group classifying extensions. That is, it classifies short exact sequences with X here, Z here, and something in the middle. So any object here naturally corresponds to an object in the X group, to an element in the X group.
How you do it?
Larger extensions are just larger extensions with more elements in between. Yes, something just longer here in the middle, and then we have X that goes back even further, and that's why the larger shift. But the cool stuff, I think this is cool, and doesn't stop here. We can go even further. We started with objects in A, but you can always also just take complexes, and then you get the hyper-X, what is usually called, and it's just a regular home between complexes in the derived. You can even go further and just collect all of this together and obtain the right derived home from any complex to any complex, in the derived at least, which is a complex such that if you take its cohomology, then you recover the X. Or more precisely, you recover the home in the derived category between Z and X shifted. In order to make this, to prove this, then the boundedness assumption helps a lot. If not, you have to assume that at least one of the complexes is bounded, and the other can be whatever you like. But if we just take both of them to be bounded, then it's the easiest case. Equally, you can define that if A has a tensor product, you can also have the adjoint functor to Hom, which will be the left-derived tensor product. Similarly, if A has enough projectives, or just more generally flat objects.
Are you thinking about some specific model of our home, like canonical resolution?
Yes.
And then you think of it really as a function.
Yes. Yes. It's sort of an internal home. Sort of. Almost. Not exactly, but.
And also depends, you'll have a model.
Yes. There is an actual construction to obtain a complex, at least up to quasi-isomorphisms in K, which taking its cohomology will naturally just be the Tor groups or objects. And we have the left-derived tensor, and it satisfies that if we start from, again, from objects in A, and we take minus n cohomology, then we just get Tor n of xy. So all of this is just packed into this derived category kind of naturally. And if we have tensor product and right derived home, then they also satisfy all the usual relations between tensor and home.
What kind of objects do you need?
Pardon?
If A has enough what objects?
Flat.
Flat. Can you say what?
Flat, that is the tensoring with it preserves exact sequences.
So can you just, I mean, this thing which you just wrote, a priori, doesn't mean something in the context of derived category? And how would you say this in language derived? I mean, this is, Tor is not something which is, I mean, so
yeah, I mean, okay, it's starting from.
It's like an adjoint to the Hom?
An adjoint to the Hom. Also, taking any two complexes, then, I mean, if you have just two complexes, then this is again a complex. And if you take the cohomologies of this complex, then you recover the Tors.
But this is something other complex. It's nothing, I mean, you need to work on low complexes to get this. You can't do this just in the derived category.
That,
if you just look at the derived Hom, then you get back to X.
yes, you get what again? Once you take cohomology of the complex, you get the X.
But I think these objects are defined only in the derived category, right?
Yes.
Defined only after you.
Yes, they are only defined in the derived category. Okay. So now we want to move on to the bounded derived category of Pn. And that is shorthand for bounded derived of coherent sheaves of Pn and over a field, say, C.
So you could also define the left-derived tensor product in the DG category.
Yes, definitely. Yes. Okay, so I want to show that in this case, then this category, then the claim or the theorem is that the bounded derived category of coherent sheaves on Pn is generated by O P n minus n O P n minus 1. That is,
What do you mean by generated?
yes.
What do you mean by open?
There is a question? Question? Generated means that the smallest full triangulated subcategory that contains these objects is equivalent to the whole derived category. That is the operations that we, these are sheaves. This is a categories, objects are complexes. Okay, so we can consider each one of those as a complex concentrated at degree 0. We can shift these complexes. Any morphism between them, we can form its cone. And then we get the triangulated category. And closing this to isomorphisms, we get the whole derived category. Okay, so this,
You never really said what a triangulated category is.
I said that, yeah, it's a additive category with the shift functor and a bunch of triangles that we call exact that satisfy certain axioms, which I don't want to get into. But basically, think of short exact sequences. If you have a morphism, then you can complete it. You can take its kernel, so that's the analog of a cone, or completing it into a short exact sequence, or exact sequence actually. So that corresponds to any morphism can be completed to a triangle. If you have two short exact sequences and two morphisms, then you have the third. Again, same thing for triangles. And basically also the quotient of a quotient is just the quotient. That is the second or third isomorphism theorem. I never remember which one. The one that says that you can cancel the denominators. Yeah.
Could you now explain what triangulated means?
I didn't hear you.
Could you please repeat the explanation what generated means?
Generated, yes. Generators as a triangulated category. That is, you take these sheaves, consider them as complexes. You can take the two operations that you have is shifting them and forming cones. That is, if you have a map from this one to this one, you can take its cone. Now you have the cone, so you can take a map from the cone to this one again, take that cone, shift it somewhere, close it to isomorphisms, take all the morphisms between all the objects, and the claim is that we got the original category.
All these forming cone they go inside which factor?
Inside the derived. Yes. And this is the Beilinson. Although we won't talk about in what sense these are exceptional. There's the dual one, yes. Actually, even further, we can also twist all of these to any degree and just take the consecutive n+1 twists, and that would also do. Okay, so before we go into proving this, then we have a bit. I need a bit more. Okay, so let x and y be smooth projective varieties over C. Then we can form the product, and we have two projections. We call this one Q and this one P. Now, taking any object M in the bounded derived category of the product, we can form a functor from the bounded derived of y to the bounded derived of x in the following fashion. If we take some complex here, then we can pull it back along P and obtain a complex here. Now we can tensor product it with the object that we chose. We still got an object here, and now we want to take the right derived push forward to get to dx. And again, I didn't discuss what are exactly the right derived and the left derived of the push forward and the pullback, but you get the idea, I hope. So we take a complex here, and we get a complex here, and it's all functorial, and it preserves exact triangles, and preserves shifts, and everything. Derived pullback, but this is flat, so it's the same. Both the projections P and Q are flat in this case. So the derived pullback and the regular pullback are the same. Or that is, the derived pullback is just pullback. OK, so we have this operation and notation that is given two complexes, one in the derived category of x and one in the derived category of y. Then we can pull them both back and obtain complexes here, and then we can tensor them. So we just denote it like this, which is just now a remark. Say we have x equals to y, then in this case we have the diagonal which is inside the product. So we can take the functor that is defined by the structure sheaf of the product inside this category. Now, so what does it mean? It means to take a complex on x, pulling it back to the product, tensoring it with the diagonal, and then pushing it forward again. This is just canonically isomorphic to the identity functor. That is, we have a projection formula, and just pulling back and pushing forward is just the identity. So the idea is now to take this functor, now back to the theorem. So if we want to prove it.
So that, I mean, when you take this left derived tensor product.
Yes.
So
basically, it's replacing.
When you then push it forward and get back the same complex.
You have the projection formula, like the usual projection formula works with no.
So when you say
for regular sheaves, you need to have locally free sheaves. But now, if you replace everything with locally free resolutions, then just have it for every object. So you have a projection formula for all objects, and using that, you get again you get an isomorphism from phi of f to f.
And the structure sheaf of the diagonal, you think of it as a sheaf on x times x. So
Yes.
you mean the
Actually,
push forward, or do
yes. Actually, the derived put forward of it. Or, yes. But all usual relations apply to the derived setting, and at least in this case where everything is flat and projective. Okay, so the trick now is exactly to take this functor of the diagonal from the derived category of Pn to the derived category of Pn, which on the face of it seems not a very interesting functor as it is just the identity functor, but to take a resolution of the functor and then getting a different expression for this functor, and then it will, after manipulating it a bit, it will become obvious that we can construct everything from just these sheaves. Okay, so we start from the Euler sequence. We will take a resolution of the sheaf, a good resolution of the sheaf, but since we're doing everything now with respect to the sheaf, that is, we want to tensor everything with the sheaf, so tensoring with the resolution will be the same, because resolutions are quasi-isomorphisms, so they are isomorphisms in the derived. So tensoring with this sheaf or with a good resolution of it is the same. And then we can split everything up, and we see that we have something easier to work with. So we start with the Euler sequence, which is 0 goes to OPN goes to O1. And this is the tangent bundle. And yes. No.
Could you remember what the maps are?
What the maps are. Tangent model, then at least on the stocks, you have at every point Cn as a vector space. So you just need to take a basis here, and this should be the diagonal map, if I remember correctly. And I think. Probably not, but I don't remember.
I think it's easy to think about it just in Cn plus 1 space. Like the OPN is a line, and the tangent space is all the rest of the stuff. It's like everything going, it's all the ways to move the line.
Yes, it's a line and it's orthogonal completion. Yes.
You might want to just say the following thing. Just take this map. This is a topological line bundle. Goes into the trivial line bundle. Okay. Which goes then to sort of the quotient.
Mm-hmm.
Okay.
It goes to omega.
Let me call it just
Okay.
something into the topological line bundle. Okay, and then you can then take Ham with O of minus 1, topological line bundle. Okay, and then you get the trivial goes to you took Ham with O of minus 1, so you get O of n plus 1. And then here you get Ham from the topological line bundle to the quotient. So you take Ham from a vector to its complement. That's just the ways you can move that vector. So that's the tangent bundle.
And Q is the cotangent bundle.
Q is
basically by definition. No?
Not sure. I mean,
No, never mind. Yeah.
It's like a quotient of the trivial bundle by the tautological bundle.
Yeah. Thanks. Okay, and now we want to twist this. So we can twist this and obtain the sequence O minus 1, O, n plus 1 goes to T minus 1. And now we have O0, H0 of O minus 1 is equal to H0, H1 is equal 0. So this means that we have H0 Pn O n plus 1 is isomorphic to H0. That is, it's just isomorphic to Cn plus 1. Also, question? Also, H0 of Pn O1 is also just Cn plus 1. So we would like to think about this one as the dual of this for a moment. And now we can consider the sheaf O1 square tensor with T minus 1 on Pn, Pn. And we can ask, okay, so what are the global sections here? And this we get by the Kunith formula that it's just Pn01 tensor with H0 Pn T minus 1. So we want to think, as I said, we want to think about it at the moment as this one as the dual vector space of this one. And then we can take the identity matrix here and take it back here. So we have a global section. So if we fix a basis, fix for a moment the basis y0, yn here of O1, then you have a dual basis. And then you can take a global section S, which is I goes from 0 to n, yi dual. So we got a global section of this sheaf, and now we can ask what is its zero locus. And it turns out that all the points if we have a point P in Pn time Pn such that Sp is 0 if and only if P lies inside the diagonal. Yes?
Correction is the X with the square around it.
Yeah.
You define it for sheaf, for complexes.
It's a tensor product of sheaves in this case, so just take one from here, one from here. Which gives us a section of the big square tensor product. Okay, so we have a global sheaf that is 0 exactly on the diagonal. In this case now, if we have a sheaf, if we have a section, then that means we have a map from O1 minus 1 dual to O Pn cross Pn goes to O diagonal goes to 0. And this is just O minus 1 square tensor omega 1. That is the cotangent bundle or the differential sheaf, whichever you want to look about it. So this is just the map defined by the global section S. So, oh, sorry. We have a map from here to the structure sheaf, which we have the diagonal as a quotient. Now, note that this fellow here is a locally free sheaf of finite rank. So actually, we have the beginning of a locally free resolution of the diagonal, because we have a locally free sheaf here and locally free sheaf here, and we just need to continue it and obtain a locally free resolution. And the way to do it is the Koszul complex O minus 1 and this is just OPN. So we've got this resolution, and furthermore, since we have a line bundle here, then the exterior power of O minus 1 square tensor with pi 1 is isomorphic to O minus k square tensor omega k k. Amit? 2 more minutes. Okay. So basically now we're just done. We need to see now that we're done, but basically that's all we need. Because now we have a finite locally free resolution of the diagonal. So tensoring with the diagonal is the same as tensoring with all of these. And since this is an exact sequence, as we can break it into short exact sequences, we can break it into exact triangles in the derived category. And then we have going through the operations of pulling back tensor product and then pushing forward, we obtain a series of exact triangles, which are, okay, so let's just denote that by LK, otherwise it will be much too long to write it. And now we can take the quotient of these two, which we'll just mark for the moment as this one, and then phi Ln F1. And we break everything to just exact triangles. And we know that we obtain here F because this is the isomorphism. So what this means that we can obtain F from these objects. We can take these two objects, and then we can take their cone. So it is in the category that is generated by these two. And then once we have this cone, we can start again on the next line. So we have F generated by all of these objects. So what this means is F is generated by the objects L, K, F. K goes from 0 to n. So it just remains to see that we can form these objects by the twisting sheaves. But if we just unpack all the definitions, this is RQ lower star. Yeah. Now, the derived tensor product, like tensor product, is associative and commutative. And again, like the tensor product, it commutes with the pullback. So what we have here is just RQ star Q star O minus K. And this is L here, but we don't need L because this is a locally free sheaf. So again, the derived tensor product is just the regular tensor product. And now we have right derived Q and the pullback of Q. So we apply the projection formula. So we have O minus K, tensor product with the right derived of the right derived direct image of the left of the pullback, which is just the right derived of the global sections of Pn. Okay, and this is just a complex of vector spaces. Actually, it's a discrete complex because between the cohomology there are no maps. So this is a complex of finite dimension vector spaces with zero differential. That is, the kth place of this complex is just a direct sum of the twisting. And it's just so if we take this complex, LK F prime, and we ask what we have in the n degree, then we just have a finite direct sum of O minus K dimension of Hn. And that's it. Yes? It's just playing with all the properties of the right and left derived. So if we have two left derived, first of all, the left derived tensor product, like the regular tensor product, you can switch places canonically anywhere. Secondly, left derived functor and another left-derived functor always commute. So if you have the pullback of these two, which is a left-derived functor, and you have a left-derived tensor product, you can take the left-derived tensor product and then pull back. Since this is locally free, then the left-derived tensor product is just tensor product. Now you have the push forward and the pull back, so you have the projection formula. And after the projection formula, you just need to know what is right-derived of the left-derived from the other direction. And if we think about it this way, then we can switch them along this side, and pushing forward to here is just taking global sections. So that's why we have global sections here. And global sections, I have to finish, is just taking cohomology.
Why is there no differential?
Because this is just the complex consisting of the cohomology at every place. And if you take one object and its cohomologies, then you don't have a differential between the cohomologies. Right? I'm pretty sure that's true.
I mean, F has some differentials. No.
F has differentials, yes. But yes, that's true.
So you take global sections of some complex. You should still have some kind of global sections differentials.
No, if you have a complex and you take its cohomology, then you don't have differentials between the cohomology. The cohomology is just graded, not a complex.
Are you just taking sections?
Mm-hmm.
So, I mean,
You have the sections from the category to the vector space, and then if you applied it to complexes, then you get a complex here, and then take the cohomology of this complex and just the usual sheaf cohomology.
would you have to resolve find F and then take you would have to sort of resolve F kind of?
Yeah.
Take the cohomology of that resolution,
Mhm.
kind of hypercohomology, and you wind up with the differentials going kind of get the second.
In the other direction.
So it seems like you would get some differential. I mean, it doesn't change.
That's okay.
It's fine. I mean, but I think you would have perhaps a non-trivial
Differential.
I mean, you're not taking the cohomology in the direction of the F complex, you're taking the cohomology in the direction of some kind of resolution of that complex.
I'll have an answer tomorrow.
That's still generated.
So let's thank.
Questions?
This doesn't change the iteration. Just there's a statement.
Yeah. So I'll have a question tomorrow, an answer tomorrow.